Okay, in order to explain to you how scientists found out Max Planck's idea was indeed correct, I first have to show you about this famous experiment, which we call photoelectric experiment, photoelectric effect. Okay, in this experiment, we have a glass vacuum tube like this, and we have two metallic plates inside at either end of this tube, and we have this lamp which can shine light onto one of the metal plates. And then when the light arrives here, the electrons will come out. Okay, these small dots are electrons, and they are called the photoelectrons because photo means light and electrons are electrons. Okay, and these electrons, photoelectrons, will move between the two plates, which means that they have velocity, and having velocity of course means there's a kinetic energy. And then when these electrons successfully arrive at the second plate, then we can read the current, because a charge moving is of course a current, and we call it photocurrent because this current comes from the light. Okay, and again we also have this battery here from which we can supply the potential difference. And of course, if you supply positive potential here, electrons are negatively charged, so they will accelerate, and then you will read higher current. But if you supply negative potential here, then electrons will slow down, and if you can adjust the potential, negative potential more or less, then electron will stop. You can actually stop them before they arrive at the second plate, and then you will see the current becoming zero. Okay, that we will call stopping potential because now electron stops. Okay, and so therefore by controlling the wavelengths of the light and also the intensity of the light, and also using different types of metal, we will try to find out the stopping potential. Okay, then what do you think? How do you think the stopping potential is related to any of these experimental parameters? And of course, the stopping potential will tell you what is the kinetic energy of this electron coming out. Okay, let's do that. Alright, let's begin the experiment with the red light, which has the wavelength 670 nanometer. And let me turn it on up to the intensity 50%. Okay, and as you can see, nothing is going on. Okay, so and then I will increase the intensity up to 100%. Still nothing's going on. Okay, so let's put it back to 50. And then now I will change the wavelengths. So the color will change down to yellow. Nothing's changing yet. Nothing's coming out. And then down to green. You see that some electrons are now starting to coming out. Okay. And then let me move this further down to blue, about 450. You can see that, okay, a lot of electrons are coming out, and you can also read the photocurrent. Okay, so here, let me first try to increase the intensity. If you increase the intensity up to 100%, remember we now have 0.028, and at 100%, you can see that current has been increased because a lot more electrons are coming out. Okay, I will put it again back to 50%. Alright, so here still quite a few electrons are crossing the gap between the two plates, and then I will try to apply the potential difference between these two plates. So I will do it slowly. Let's first put minus 0.2 volt. You can see that, okay, some electrons are slowing down. Okay, they cannot arrive at the plate, so they are pushed back. So the current has been reduced, and well, this current meter cannot read very small numbers, but still some of them are arriving. So current is actually not zero here. So let's continue to change it down to minus 0.3. Okay, this guy is still arriving, so I will change it further down to minus 0.4. You can see that some are still okay, cross the gap, so I will move it up to minus 0.5. Okay, you can see that. Okay, finally none of the electrons are arriving near the plate, so finally the current has become 0. So the potential at this position, at this situation, is called the stopping potential. So now the stopping potential is minus 0.5. Okay. And then in this case, what will happen if I change the intensity up to 100%? Since we are shining a lot more light, a lot more energy will be transferred to these electrons. And do you think some electrons will arrive at this plate? Let's try that. If you change up to 100%, you can see that a lot more electrons are coming out, but none of them are arriving. Okay, the stopping potential apparently does not depend on the intensity of the light. And then how about frequency? Okay, what if we change the frequency? If I change the color down to purple, which has a short wavelength, you can see that, okay, some of them are arriving, and then you can again see the current. So in this case, we have to enhance the negative potential, go to minus 0.6 or even minus 0.8. You can see, right? Just barely. Okay, now maybe, okay, this is a good number, but maybe let's try something like this. Then, indeed, none of them are really arriving. Okay, now it means that if you are at the wavelength 397, now the stopping potential will be minus 0.81, which is different from the value we had. So it actually tells us that the stopping potential, which is actually the maximum kinetic energy of the electrons, depends not on the intensity of the light, but on the frequency of the light. Okay. Then one more thing, we can actually change what kind of metal we have here. Actually, in the beginning, it was selected as a sodium. Okay. Now let's try to change this to zinc. We have a lot of options, but let's try zinc. If you do that, all right. Now, okay, no electrons are coming out, right? Okay. So in this case, okay, let's put this BIOS back to 0. Still nothing's coming out. And then what do you have to do in order to make the electrons come out again? We have to change the frequency. Okay, let's go down further. Okay, here. Okay, now finally, around 260 nanometer, electrons are again starting to coming out. And then, again, if you apply a negative potential here, for example, minus 1, then not enough, maybe, or you can actually go up to, oops, I'm sorry, made a mistyping. Yep, okay. So up to here, minus 0.3, still crossing. So, maybe not enough yet. Oh, maybe enough. Not. So let's change up to minus 0.5. Okay, this is enough. This looks like the stopping potential at this position. And again, if you still make the wavelengths even shorter, you see, okay, some of them still arrive, and in that case you have to again enhance the stopping potential. Okay, in this case it's not enough, so let's try that. Still not enough, so therefore okay, looks okay. Okay, so which means that now if you have a different metal, then the wavelengths at which the electrons are starting to coming out look different. But then the fact that given the metal, the stopping potential depends only on the negative or it's only on the wavelengths, but it does not depend on the intensity. Okay, so we will try to explain and summarize in the next slide. Okay, so let's try to summarize the result of the photoelectric experiment that we have seen in the simulated experiment. Okay, and this is more like a real experimental setup. Okay, so this is the vacuum tube, and then the light comes in like this and hit the metal target T. Then photoelectrons will come out because they gain kinetic energy, and because of this kinetic energy they will move across the vacuum and arrive at the collector C. And then the photocurrent was recorded. Okay, and then here we can also apply the potential using this battery or the EMF device. And then if you apply the negative stopping potential or minus V stop to the collector C, then the photocurrent finally became 0, right? Okay, so what it meant was that the kinetic energy of the most energetic electrons, or the maximum kinetic energy, Kmax, was actually equal to the charge of the electron multiplied by the stopping potential. Okay, this is what we knew. And then we performed several experiments, changing many variables. The first thing we saw was that this stopping potential does not depend on the intensity of the light. Okay, that was the first thing. And then we tried to change the wavelengths, which actually means that we have changed the frequency. And what we found was that this V-stop, stopping potential, depended on the wavelengths of the light. So therefore, it actually means that it depends on the frequency of the light. Okay, you remember how these were related. So C is equal to F lambda, so they were inversely related. And then if you plot the result as a graph, it looks like this. Okay, so if you go to higher stopping, if you go to higher frequency or small wavelengths, then you can see that the stopping potential is increasing. So overall, they look like a linear line. And then if you go below certain frequency, then there is no stopping potential, which means that the electrons are not coming out. So this frequency, we can call it actually cutoff frequency. Okay, this cutoff frequency below which photoelectrons cannot be ejected, and this one actually below this frequency. For example, here, if you are over here, however strong light you may send, the electrons will never come out. Okay, and this value, this cutoff frequency, actually depends on what kind of metal target you have. We saw that it was different between the sodium and the zinc. So therefore, it is a property of the metal itself. And if you multiply by the Planck constant, this again becomes an energy. So we actually give it a name work function. Well, you don't have to know the details about the work function. Just try to understand that this depends on what kind of metal target you have. But the important thing is that if you perform and repeat this measurement several times using different type of metal like cesium, potassium, sodium, lithium, like here, all of them have different stopping potential, but nevertheless, the slope of this curve of the stopping potential as a function of frequency is actually exactly the same. This is very important. The slope of V-stop will be constant regardless of the type of the metal. Okay, so this was what people or scientists already knew by the experiment. And finally, it was Einstein who explained this. Actually, he used the idea of Max Planck's energy quanta. Okay, just remember that Max Planck, when he was trying to explain the thermal radiation from black body, he assumed that the elementary energy of the thermal radiation had a energy which is proportional to the frequency, and he used the proportionality constant H, which we call now the Planck constant, right? Okay, and then Einstein actually used this idea and then assumed that it is actually the light itself which contains this energy. So therefore, by using the simple idea of the conservation of energy, the energy HF, which is provided by the light, actually becomes the energy of the electron plus the energy lost during this collision process. Okay, so the kinetic energy, which is a K max of the electron, is simply the elementary charge multiplied by the stopping potential, and then this term is simply the work function, which actually is the energy loss of the electron at the surface. And then you can rewrite this equation and then write it this way. Okay, now the V stop is expressed in terms of the frequency, and this is like a linear function. So therefore, the slope of this line is h divided by E, which is here. Remember that Planck constant is just a constant, and elementary charge is same regardless of the type of the metal. But this number, which is a work function, depends on what kind of metal you have. So if you perform this experiment with different metal, then the position where this line crosses the horizontal axis will be different depending on what kind of metal you have, but the slope of this line will always be the same. Okay, so from this idea, by combining Max Planck's light quanta and conservation of energy, Einstein successfully explained that why we have the same slope regardless of metal, and in doing so, he really established the idea that light itself has an energy quanta, and then from the fact that the conservation of energy works, he really proved that this small amount of energy of the light works just like a particle. Okay, and then now we call it photon. Okay, and Einstein, of course, didn't stop there, and he proposed a new thing. You know, this collision between the light and the electron is just like a collision experiment we have seen before. So therefore, the conservation of energy was satisfied. But there's another thing that has to be conserved during this collision process, which actually is the linear momentum. So therefore, from this idea, Einstein proposed that this quantum of light, photon, has a linear momentum. And it is actually a very surprising idea, because the linear momentum, which we typically know as mass multiplied by velocity, you know, it requires the mass, but light does not have mass. How come does it have any linear momentum? Actually, what he suggested was that for the light, which does not have mass, the momentum must be energy directly divided by the velocity, which is c. This was Einstein's idea, and then I'm not going to explain the details, but anyway, if you rewrite this, actually what you get is now the Planck constant divided by the wavelength. Okay, so which means that when photons interact with matter, like electrons or anything else, the conservation of both energy and linear momentum will now have to be satisfied. Okay, and then of course this was a very surprising suggestion when Einstein first proposed it. So therefore we need the experimental evidence, right? Okay,